right? Here we click OK, and yes. Should I start already, or we wait for?
Will we wait or do we start?
Let's wait 1 more minute.
Sure.
Because Daniel is back.
Hello everyone, thank you for joining. Today, with us is Filippo Camilloni. He comes from Frankfurt, Germany, and I will read a small bio he sent me. He obtained his master's degree in theoretical physics at the University in Perugia, Italy, with a physics on string theory and holography applied to the study of electric transport properties of graphene. Then he took a joint PhD degree between the Niels Bohr Institute at the University of Copenhagen, Denmark, and the University of Perugia, Italy. His thesis focused on theoretical astrophysics, mainly investigating force-free electrodynamics, force-magnetic mechanisms, and relativistic magnetohydrodynamics with analytic techniques. From 2023 to date, he's part of the relativistic astrophysics group of Luciano Solar in Frankfurt, Germany, and member of the DSF collaboration, continuing his investigation on the vision of the relativistic jets. So, thank you very much, and you can start.
Thank you very much for the introduction. And first of all, I would like to thank Alejandro for hosting a portion of the Relativistic Astrophysics group in Frankfurt, and also you for organizing this AstroLunch. So today I'm going to speak about the possibility of using relativistic jets as strong gravity probes for spinning black hole backgrounds. And this is an idea that we recently explored together with, sorry, I have some problem, that we recently explored together with Luciano in our latest paper, but that also builds upon previous results that I've been obtained in the course of these years, and that I would like to review while trying to give a broader perspective on the subject. So I guess pretty much everyone here is familiar with what a relativistic jet is. Essentially, these are extremely energetic and collimated streams of plasma, which propagates for impressive distances in the extragalactic medium, and whose origin has to be traced back at the galactic center from which they originate, and which we know hosts supermassive black holes. We know this also because we recently observed two of these actually with the Event Horizon Telescope collaboration. And we have to realize that whenever we look at this kind of images, what we are also doing is zooming in towards the regions where the jet is emitted in first place. So by analyzing this kind of pictures, we can understand many important features of the emission mechanism. For instance, we can understand that the light coming from this region is polarized, as signaled by this polarization pattern, these stripes pattern here. And the polarization has a smoking gun signature for the presence of a strong and ordered magnetic field in the black hole environment. And this supports the hypothesis that a key element for the emission of the relativistic jet is indeed the presence of a strong magnetic field, and which extract the black hole rotational energy through this so-called Bland-Forrest-Nayak mechanism, which will be the main character of my presentation, and that I will review in a second. But even in those cases in which we do not directly observe a jet, still the magnetized environment around black holes seems to be responsible for a very interesting phenomenology. And this is the case, for instance, of Sagittarius A star, which is characterized by an intense flaring activity that we now attribute to the occurrence of magnetic reconnection events at scales comparable to the event horizon scale. So all of this points out to the idea that there is a very interesting and complex dynamical interplay between the magnetized environment and the black hole strong gravity. And the emission of relativistic jets, the Bland-Forrest-Nayak mechanism in particular, is an example of this interplay in which a strong magnetic field that we call a magnetosphere extract the black hole rotational energy. Now, we are used to think in general relativity about energy extraction mechanisms, typically by referring to the standard textbook example of the Penrose process, which in its original version, called the mechanical Penrose process, involves, I don't know what to do for this, sorry, involves point-like particles. So in this example, we have a point-like particle which approaches the black hole and enters the black hole ergosphere, where it decays in two other particles. And because of the properties of the ergosphere, one of the particles is created with negative energy and falls into the black hole horizon. The other particle, by means of energy conservation, will escape at infinity with an additional energy, which must come directly from the black hole rotation. So this is the basic idea of the, let's try to switch this. Thank you. Am I still, no, allow? I think I also have to share again. Yeah. So you have to see the animation again, unfortunately, I'm sorry. But it seems to be more stable. Okay. As I was saying, this is an example of one mechanism which realizes an energy extraction from a black hole. But it is important to realize that the Penrose process, as it formulated in its mechanical version, is not the only possibility, and actually is very unlikely to occur in real astrophysical scenarios. But we can speak more broadly about generalized Penrose processes, like any kind of physical process which involves a negative inflow of energy of some type towards the black hole horizon, to which corresponds a positive outflow of energy towards some future time slice. So the idea is that the general relativistic picture remains always the same, but what really changes across different scenarios is the agent operating the energy extraction. In the case of the relativistic jets and of the Bland-Forrest-Nayak mechanism, this agent is provided by a magnetosphere, which co-rotates together with the black hole in such a way as to continuously tap its rotational energy and power and sustain the emission of the relativistic jets. So this is, in a sense, the blunt-force-Nyack mechanism. We can think about it as a purely electrodynamical manifestation of the Penrose process. Other astrophysically interesting mechanisms have been recently considered in the literature, and I will briefly mention one that involves the possibility of magnetic reconnection. But coming back to the blunt-force-Nyack mechanism, now the idea is that the jet luminosity is directly related to the power extracted in this mechanism. And both analytical and numerical computations converged to the same exact expression for this power, in which every single element has a specific meaning. So for instance, we have global prefactor kappa, which is purely associated to the magnetic field geometry. So this is just a number that will change whether we are talking about monopolar magnetic field or a paraboloidal one, for instance. Then the energy in the blunt-force-Nyack mechanism flow along the open magnetic field lines which thread the black hole. It is therefore reasonable to assume that the more magnetic field lines we have, the more energy we can extract. And there's the reason why we have dependence on the horizon magnetic flux psi-h, which is in some specific scenario like magnetically arrested accretion disk, is directly related to the accretion rate. And finally, of course, we are extracting rotational energy. And so the more the black hole is spinning, and the more energy is available to be extracted, so that there is a dependence also on the horizon, on the black hole angular velocity. And this quadratic scaling that you see here is essentially the original formula that was derived by blunt-force-Nyack in 1977 at the leading order in a certain perturbation theory. But if the black hole is actually in the high spin regime, this formula must be corrected, and we need to include additional terms. We need to correct this formula with the inclusion of this high spin factor, a certain function f omega, which is different from 1 only for black holes in a high spin regime. And this high spin factor is typically expressed as an expansion in the black hole angular velocity, and actually is very interesting for us because it seems that the coefficients of this expansion are completely independent on the specific characteristic of the magnetic field. And therefore, actually, we showed with a concrete example in modified gravity that these coefficients might contain strong gravity informations about the black hole background that launched the jet. And this brings me immediately to the question that I would like to address at the end of this talk. Namely, assuming that we have independent measurements over the jet luminosity and the black hole angular velocity, it is possible to understand whether the jet emitting a relativistic jet is a Kerr black hole as predicted by general relativity, or something else coming from an alternative theory of gravity. And the way we answered this in our latest paper is by constructing the very first theory agnostic model for the blunt-force-Nyack mechanism. And the answer is yes, under certain conditions, we can distinguish whether this black hole is from general relativity or something else. But before understanding this, we need to clarify what is the appropriate electrodynamical framework in order to study the blunt-force-Nyack mechanism and the problem of black hole magnetospheres in general. So we have said that the black hole environment is characterized by the presence of plasma, magnetic fields, and in particular, if we focus on magnetospheres, which are the agent operating the energy extraction in this context, the magnetospheres are regions in the black hole environment in which the magnetic fields are so intense that they completely overwhelm the plasma in the energy momentum balance. Under this approximation, it is actually possible to recast the equations of general relativistic magnetohydrodynamics and construct an independent theory, which is called force-free electrodynamics, which is the appropriate theory to study the magnetospheric problem. And force-free electrodynamics is actually a very interesting and rich theory from a mathematical perspective. From the equations, you can immediately notice that actually only the electromagnetic field enters as a dynamical quantity, but this must not be confused with vacuum because the plasma is still present and it is important to screen the longitudinal components of the electric field and sustain the magnetic field. But the point is that it only plays a passive role. So the dynamics here is entirely governed by the magnetic field lines, which move in a curved background geometry associated to the black hole. And the plasma will passively follow these dynamics. So maybe you can notice also from this force-free constraint that these equations are highly nonlinear, and so it doesn't come as a surprise that we don't know any relevant, exact, physically interesting solution in a curved black hole background. So what we can do in order to approach this system of equations is by either performing numerical simulations, and I will show some example with particle in cell simulations, or using perturbative analytic approaches. And while I'm mostly interested in the analytic side of the story, it is still interesting to make comparisons with the numerical results. And to this regard, the group in Frankfurt and Main, and when I say the group, actually I'm referring to Claudio, developed a new general relativistic particle in cell code, which is capable of simulating the dynamics for a large number of particles and strong magnetic field in a curved background geometry associated to a black hole. And therefore, this code, FPIC, is capable of simulating the magnetospheric model around black holes. And you can see an example of these simulations in this snapshot with the plasma density on the left and the Lorentz factor on the right. And I will often refer to this snapshot because, in my opinion, it clearly illustrates what is the physical processes occurring in a black hole magnetosphere and the black hole magnetosphere structure. And it also gives me the opportunity to show how the numerical results and the analytic approach can go hand by hand in studying this problem with the analytic approach, which are fundamental if we want to derive theoretical predictions, and the numerical simulations, which are crucial in order to test this prediction and extend them to the highly nonlinear regime. So yes.
I think that might be true or not, that the spin vector of the black hole is aligned with the spin vector of the torus. Is that correct? Or they have
a misalignment?
Any orientation? So how does that model or that simulation is done?
So thank you for the question. Actually, you are referring to a torus, but here there is no torus occurring. So this is a purely magnetospheric model, let's say. But in a realistic scenario like those associated to M87, for instance, we indeed expect an accretion disk to provide the plasma and the magnetic field. In that case, you have a torus, yes. And typically, the assumption, and it is an assumption, is that the black hole spin is aligned or or completely misaligned with the black hole torus. But there were also studies in GRMHD, for instance, by Chekovskoy and other people that tried to understand what happens if we have a misalignment between the two. And the physics is very interesting. Like the jet is characterized by a much more turbulent state, which is called a striped jet. So yeah, this is a very interesting question to understand, actually.
The power equation that we do first, in which you have the angular velocity of the black hole, then there should be another term in which the two spin vectors should be interrelated somehow.
Yeah, in that equation, in that equation, which is maybe I can write it. It's more simple. So we have the power, a certain prefactor, and let's forget about this actually. But yeah, so everything about the torus enters here, enters in how much the accretion process is providing magnetic flux to the black hole. So in deriving this relation analytically, I always assume that the torus, I mean, the whatever is providing, yeah, yes, exactly. But if something changes in this regard, I expect to change it here. Okay. Should I continue? Okay. Yes, so let's come to the analytic side of this story. What we can do is to indeed assume that we have a stationary and axisymmetric magnetosphere. So in this case, it is possible to show that the electromagnetic field strength can always be rewritten in terms of three physical quantity, each with a proper interpretation. So for instance, psi is the magnetic flux around the black hole, which is a function which is constant along the poloidal projection of the magnetic field lines. Then we have a certain function I, which is called the poloidal current. And by means of the Ampere law, it will be associated to the toroidal components of the magnetic fields. And of course, if we are talking about a spinning black hole, we also expect that the magnetic field lines will start to acquire a certain angular velocity. So that this angular velocity for the magnetic field line is actually associated to the generation of electric fields in the black hole magnetosphere. And the idea is that to solve the magnetospheric model, we need to understand explicit functional expressions for these three quantities. And the way we do this analytically, as I said, is by resorting to a perturbative expansion. So in particular, we consider the black hole as if it's slowly spinning and perform a perturbation theory for small black hole spin A star. So the idea is that we start by constructing some magnetic field configuration around a Schwarzschild black hole, a static black hole, let's say. And here, once you have this, you basically have to specify the magnetic flux function. You will not have any toroidal component. You will not have any angular velocity because the black hole is non-spinning. Then, once we have this, we turn on a small black hole spin. So in other words, we let the black hole spin and drag into the spinning motion also the magnetosphere, which mathematically means that we are considering perturbative corrections in the black hole spin, which are associated to the presence of a toroidal magnetic field and to an angular velocity of the magnetic field lines. We can plug all these expansions into the equations of force-free electrodynamics, and what we can derive is a perturbative expression for the Blunt-Forrest-Nyack power. So this is the general strategy that we follow. So we need to start from some static magnetic field configuration. And here, actually, you have an infinite amount of possibility. But the simplest configuration you can choose is the so-called split monopole magnetic field, which is a purely radial distribution of the magnetic field lines that we reverse in polarity across the equator so as to maintain the divergenceless of the global magnetic field. But there is a price to pay in order to perform this split. And the price to pay is that we are introducing a discontinuity in the equatorial plane. But rather than being a flaw of this model, this is actually an advantage because this discontinuity is called a current sheet and is present in every sort of magnetospheric model around every kind of astrophysical object. For instance, the sun corona is full of these current sheets. And current sheets are extremely interesting from a physical point of view because these are unstable structures subject to magnetic reconnection. So what can happen if we, assuming that we are zooming in towards this region, what happens is that close to a current sheet, we have two oppositely directed, two magnetic field lines with opposite polarity. And what can happen because of like perturbations in the plasma velocity or something like that is that the two magnetic field lines make contact with each other and establish this reconnection X point configuration, which is the true onset of magnetic reconnection. Once this occurs, we can have a sudden rearrangement in the topology of the magnetic field lines, which releases the magnetic energy that they store by converting this energy into two oppositely directed plasma outflows. So this is the basic picture of magnetic reconnection that, as you can guess, is a highly nonlinear process. And in the in the latest stage of the reconnection, what we actually observe is the formation of coherent plasma structures, which are called plasmoids, which are the blobs that we are observing in this video. So black hole magnetospheres naturally develop these plasmoid chains, these current sheets that evolve into plasmoid chains. And in the plasmoid chain, the plasmoids are highly dynamical objects that can interact with each other. For instance, they can collide and split to form other two plasmoids. And it's because of this that people started to think whether magnetic reconnection and plasmoid formations can be considered a possible candidate for a new version of a Penrose process, which is very reminiscent of the original mechanical Penrose process. So in this magnetic reconnection-driven Penrose process, what happens is that somewhere within the ergosphere of the Kerr black hole, magnetic reconnection kicks in. Two plasmoids are being created. One with negative energy falls into the horizon. The other with positive and additional energy escape at larger distances, where at some point it will explode, causing one of the flares that, for instance, we observe around Sagittarius A star. So we studied this mechanism analytically, and actually we found that in principle it is possible, and it is an active mechanism, whether under the assumption that the magnetization of the black hole environment is high enough, and the black hole is sufficiently spinning. And under these assumptions, you can extract some consistent power of the jet luminosity. And actually, we also have shown that our numerical simulation seems to support this idea. So what I'm showing you here is a space-time diagram in which the world lines of plasmoids are represented as peaks in the plasma density. And I highlighted with the two red circles two events in this space-time diagram in which we observe two plasmoids being created, one outgoing and one ingoing. And it is interesting because this is the same kind of scenario that we are modeling here. And it is interesting to analyze this same space-time diagram from a different perspective, from the perspective of the energy at infinity of the positrons, for instance. And we find that these red circles precisely corresponds to transition regions where particles start to acquire negative energy. And having negative energy is a necessary condition in order to have any sort of energy extraction mechanisms from black holes. So it seems that these numerical simulations support this idea of the magnetic reconnection-driven Penrose process, but further investigations are needed, of course. But coming back to the relativistic jets and to the Blandford-Znaeck mechanism, now we have constructed a spinning black hole magnetosphere. We have that our magnetic field lines are spinning together with the black hole, but this behaves like elastic strings around the black hole in a certain sense. So it is actually possible to identify two interesting regions in a black hole magnetosphere, which are called the light surfaces, where this rotation of the magnetic field lines becomes superluminal, meaning that the particles cannot simply follow the magnetic field lines here, but have to acquire some radial component of their velocity. These inner and outer light surface are an intrinsic characteristic of the black hole magnetospheric model, with the inner light surface, which is always contained within the ergosphere, and the outer light surface, which basically plays the same exact role of the pulsar light cylinder, if you are familiar with the light cylinder process in problem in pulsar magnetospheres. And for us, it was interesting to notice that this outer light surface scales actually in a non-perturbative manner with the black hole spin parameter. And this signals that if we want to extend this perturbation theory to high orders, then we need to enhance this perturbation theory with something else, which is a matched asymptotic expansion scheme. Basically, the way it works, this is an analytic technique that we developed in this context, and the way it works is that we construct two independent expansions, one expansion in an inner region close to the inner light surface, and other independent expansion in an outer region close to the outer light surface that we need to resolve by appropriate redefining a certain radial coordinate. Then we can imagine that if the model is working, then there is an overlap region in which both the expansions are valid at the same time. And indeed, we expect that at each order of the perturbation theory, every term of this expansion will match precisely each term on the other side. And this is precisely what we have shown in the case of a Kerr black hole, where you can see with the colors how the various terms match precisely each other. And this is the only possible way of constructing an high-order black hole magnetospheric model in an analytic manner. And this is, as I said, what we did in the case of general relativity for Kerr black hole. So I will first show this analytic result, and then I will extend this in a theory agnostic manner. So what we have done by means of the perturbation theory and the matched asymptotic expansion scheme is essentially computing this high spin factor F in the case of general relativity. And I highlighted in red the terms that we added first by means of the matched asymptotic expansion procedure. And at this point, we have a high-order analytic prediction, and it is therefore interesting to compare with the results of the numerical simulations, which is what I'm showing you in this plot. And you can see that here the red line is the analytic curve derived from the formula above. And the points are the data that we computed from the simulation by computing the Poynting flux and averaging in time to obtain stationarity, a stationary result, let's say. And the matching between the two is kind of impressive. And it is also more impressive to think that in principle we have constructed this formula by assuming that the black hole was in the slow spinning regime. But the agreement between the analytics and the numerics is very good even when the black hole is highly spinning. So it seems that this analytic procedure that we constructed points out to a large convergence radius for the Blunt-Forest-Nyack perturbation theory. And as far as I know, this is for the moment the best analytic model which was confirmed with the simulations for spinning black hole magnetosphere. So given that our method works, we would like to extend this and understand whether how this formula changes outside general relativity. So extending this in a theory agnostic manner. And the way we can do this is by repeating essentially the same computation in the so-called Konoplia-Rezzolla-Zhidenko metric, which is a theory agnostic black hole metric. Theory agnostic in the sense that this metric is not a specific solution of any theory of gravity. It's just a parametrized metric in which we have an infinite number of new parameters in addition to the standard mass and spin parameter of the Kerr black hole. These are called the KRZ parameter, and every parameter essentially regulates a certain characteristic of the black hole. For instance, rho is associated to the horizon radius and will also affect the black hole angular velocity. In this context, we introduce a new space-time classification for the KRZ black holes that allows us to distinguish sub-Kerr black holes or super-Kerr black holes, depending on whether their angular velocity is smaller or bigger than the corresponding angular velocity of a black hole in general relativity with the same black hole spin. And sorry, I know this is a bit annoying. Yeah, and this is very important for us because, as you can see, the Blanford-Nayek power directly depends on the black hole angular velocity. So this gives us something to compare. We want to compare Kerr black holes in general relativity with sub-Kerr and super-Kerr black holes. And we also constructed a new quantity, which is this quantity delta, which essentially quantifies what is the deviation of, when we turn on a certain subset of the KRZ parameter, what is the deviation in the space-time that we are observing. So this is giving us gauge invariant quantification of what it means when we set a certain parameter equal to a certain value. So we can now repeat the same exact computation that I showed you before, compute the high spin factor in the KRZ space-time, and what we obtain is something like this, which is a theory agnostic prediction of the Blanford-Nayek luminosity. Yes? No. Sorry. Okay. Let me arrive at the end of this slide. No, I think, thank you for letting me clarifying this. I think that the original metric that was derived was indeed a non-rotating metric, and it's called the Rezzolla-Zhidenko metric. The Konoplia-Rezzolla-Zhidenko is the extension to spinning black hole spacetimes. So, and indeed, you can see that we still have a spin parameter here, which is A star. Yes, no problem. And yes, and in particular, this version that I considered in this paper is also more restricted in the sense that it's in horizon penetrating coordinate, which is something that in any case we expect for black holes. We expect the horizon to be like a coordinate singularity, right? So yes, so this is the expressions that we derive and that extends the Blanford-Nayek theory in a theory agnostic manner. And it's theory agnostic because all the KRZ parameters enter in this expression through these two functions, R22 and R42, which are directly related to the magnetic flux of around the black hole. And we can actually compute explicitly this the functional behavior of these quantities by, for instance, using a simple shooting method. This is the method that I used at least. And we found that as far as the KRZ parameter are small enough, we can always approximate quite good this functional dependence with a quadratic polynomial. So, but with this analytic prediction, now we can make real comparisons and answer the questions that I asked at the beginning. which is what I'm showing you here. So here we consider three different curves. Is an example in which we set the KRZ parameters in such a way that we obtain a subkerr black hole in blue, a superkerr black hole in red, and of course, when you set all the KRZ parameter to 0, you just recover the general relativistic case. And we chose these parameters in such a way that the deviation that they cause in the space-time, quantified by delta, is comparable between the two cases. And what we observed here is kind of interesting. So as far as we are in a slow spinning regime, yeah, but maybe now it's stable. So yeah, let's try like this for the moment. So as far as we look at this plot in a slow spinning regime, so when the black hole is in a slowly spinning, the Blunt-Forest-Nyack mechanism can be well approximated with a simple quadratic scaling. But this means that we can never distinguish black holes in this region. And this is clear, in a sense, because this points to the fact that the angular velocity of the black holes is an intrinsic degenerate quantity. As I show you here, different black holes can have the same exact angular velocity, but totally different KRZ parameters. So for instance, we can choose rho and A star in a different combination and produce the same number. So omega h alone cannot allow us to understand whether the jet emitted by this slowly rotating black hole is coming from general relativity or not. But we can extend the result to the high spin regime like we did. And at this point, what is important is that the high spin factor becomes relevant. And this high spin factor is precisely what contains the strong gravity information about the background. And indeed, we can see that we can distinguish the different cases. We can, for instance, notice that superkerr black holes are always emitting a brighter jet compared to their counterpart in general relativity, or subkerr black holes are always emitting a dimmer jet as compared to general relativity. And actually, superkerr black holes can also probe regions in this diagram which are totally excluded by general relativity, because this would violate constraints that we have in that theory. So this seems to answer the questions that I wanted to ask, namely, it is in principle possible to use the jet luminosity to understand what kind of black hole we are looking at, if and only if the black hole is in a high spin regime, is sufficiently spinning. And actually, we did something more in the sense that, as I showed you before, these functions, which contains the dependence on the KRZ parameters, can actually be well approximated with quadratic polynomials. So what we can do is to make the explicit expression for the high spin factor more humane, in a sense, by writing them as a double expansion in the black hole angular velocity and in the KRZ parameters. And this allowed us to construct the first, if you want, theory agnostic catalog, which tells us what is the jet luminosity when we turn on a certain value of a single KRZ parameter. And this is a bit of an advantage compared to numerical simulations, because let's imagine you want to do the same with numerical simulations. Here you have to scan for every point in this parameter space, you have to scan every point with one very expensive simulation, typically. So this is just to say that I'm not competing against the simulations, but that analytic approaches can be a nice complementary approach that we can use. So with this, maybe I can conclude. So just a very quick recap. What I showed is that there are active electromagnetic energy extraction mechanisms in black hole environments. we expect that the Bland-Forest-Nyack mechanism is that associated to the emission of relativistic jets, but people started to considering also the possibility that magnetic reconnection can be another possibility that can explain some of the most powerful flares around Sagittarius A star. And in the context of the Bland-Forest-Nyack mechanism, and the jet emission I showed you as the analytic and numerical approaches can go really together in constructing a coherent picture of the black hole magnetosphere, and that apparently there is a rich space-time strong gravity information contained in one important piece of the Bland-Forest-Nyack formula, which is valid when the black hole is in the high spin regime, and that in principle can allow us to understand and to test general relativity with strong gravity observations. So thank you very much for the attention.
Thank you very much, Filippo. Any question? I was wondering about the scarcity parameters.
Please, sorry?
The scarce set parameters that you
Yes, yes.
way of parameterize, so I call it a theory agnostic approach.
Yep.
If there are also dependent constraints on these parameters, for example, certainly you obviously modifying the metric coefficients, you'll be changing the curvature scalars of the overall space-time. There might be some causality limits there. You can't just pick them in a complete arbitrary way before starting to travel back in time.
Yes, yes, yeah.
And also another set of constraints might be things like looking at lensing effects.
Yes, thank you. This is actually a very important question, and we did derive constraints in our paper in order to understand what type of this, because the problem is that the KRZ the metric is too generic. Exactly, but I mean, you expect, of course, some constraints. Just look at the event horizon size. Here, rho cannot be below -1. That's one constraint, for instance, but there is also an upper limit that we derive by imposing that a certain function of this metric gives this as maximum, the solution with the maximum radius, which is what we expect in order for this to be the true event horizon size. So that's very important, actually, to constrain the KRZ metric, and is an active field of research that people are trying to do, either with observations or with purely theoretical approaches like we did in this case. Yes.
Yes, I remember that from Narayan or Chekhoskov's paper, they compute this F numerically.
Yes.
And compare with the Bland-Forest-Nyack formula.
Yes.
They say that, of course, the Bland-Forest-Nyack formula is very rough approach to the more realistic scenario that we can say more realistic scenario is coming from numerical simulation. They are expensive. So the more correct formula, let's say, is coming from numerical simulation. So
absolutely, yes.
Then they did some corrections, some extra terms into this function. But my question is how much you are confident on your calculations in comparison to numerical calculations, because
yes, I got a question.
The Bland-Forest formula in Chekhoskov's is have some errors, let's say, and the errors or the differences, we can say difference, maybe is the best word. The difference between numerical and analytical are, let's say, small. But now, introducing RZ, you also have more or less the same order of differences. So how you can distinguish that these differences is coming from different space-time or from this approximation that you are doing to solve your equations analytically?
Yes, thank you.
Sorry,
That's
I'm
a
not sure it was clear.
no, that's a very clear and very interesting question. So first of all, I would like to make some comment on the work of Naraya and Tchaikovsky, which was the entire starting point of my PhD, let's say. So what they did is indeed to notice that there was something off with the standard Blunt-Forrest-Nyack formula in the high spin regime. So this term was already computed analytically. And what they did was to compute essentially this number by providing a fit of this formula. So what we did instead was by computing this number and other numbers in a self-consistent manner. And we showed, I don't have actually the picture here, but we showed that I made the comparison with the Tchaikovsky formula. And even when we are very close to the extreme regime, my analytic result doesn't differ for more than 5%. So it's kind of accurate. And we can, in that case, in that specific scenario, we can really understand how good is the analytic result compared to the numerical one, which are, I agree with you, are the true one that we should consider. In the case of KRZ, the point is that we don't have simulations of this in this regime. So actually, this was a first proof of principle, let's say. Is it possible in principle to understand whether we can distinguish black holes with jet luminosity? And if it is possible, under which conditions? We answered this question. Then I agree with you. We don't know how good is this analytic result in this regime. And for this, it is actually very important that a numerical simulation try to scan this region and make comparison with the analytics. I totally agree with you. Only in that case, we can at that point understand how good this approximation is. But I'm confident enough because I made the comparison with Tchaikovsky in the GR case that this formula is actually quite good even when the black hole is in a very high spin regime. Of course, there are also in this case, there are a number of assumptions that enters in the game. Like there are different KRZ metrics that were considered in the literature. We have chosen one. And we derive constraints for that one. If you change the metric, something different appears, maybe.
Can you go back to the slide of the space-time solution?
Yes. You mean the KRZ metric?
Yes.
Yes.
Yeah, right. These parameters, A1, B1, are the same of the Redstone space-time because or do the solution change when you consider the spin?
I'm not sure I got the question. Can you rephrase it?
That's because then we have the Redstone space-time, the original solution, which you have these series defined in terms of these coefficients.
Yes, I see what you mean. Yes, these are the same exact parameters. So the only difference is that the constraints that you derive on the parameters, sorry, I rephrase. There are constraints over the values that these parameters can acquire in order for this metric to be physically relevant, like we were discussing before. And these were already derived in the Rezzolla-Zdenko case. What we did is to extend these constraints to every black hole spin. But yes, the parameters are exactly the same.
You're just like a first order.
A first order what?
Yes, in this expansion.
Here we are not performing any expansion.
No.
Sorry.
Yes, in the Redstone solution. You only consider the first term.
Yes. If you think, yes, the Rotzola-Zhirhenko solution directly emerged from this metric if you set A star equal to 0. So it would be the first, yes, the first order in a perturbative expansion for small spin, for instance.
If not, we thank Filippo again.
Thank you very much.